In this video, we are going to continue to discuss the domination relation and dominance frontier relations and how to implement them. So recall that the domination relation is defined as such. A dominates B if all passes from the initial block to B, with each A in between. And we define the set of dominators of B as follows. Dom B is the set of A, such A that A dominates B. So it is the very definition, and the useful property to efficiently calculate the domination relation is this second property here. If a block B is not the initial block, and we know that there uniquely exists a block A, which is the dominator, and the dominator of B is the union of A and the dominators of A. So in that sense, A is the canonical or the most closest dominator of B, and as a result, we are going to say A is the immediate dominator of B. And from this relation, we can immediately see that the A is the dominator of B if and only if A is the immediate dominator, or it is the immediate dominators, etc., etc., etc. So if A is one of these recursive intermediate dominators, then A is the dominator. It is the basic property we are going to use in the efficient construction of domination relations. So recall that thanks to this property, we can build a domination tree where a parent is the immediate dominator of children. So we can construct that using these properties. So this is definition. The dom tree of G from the initial block I is a tree in which the parent of a node A is the immediate dominator. And we're going to construct this domination tree using this equation. Immediate dominator of block X should be the intersection of the immediate dominator of the predecessors of this X. So here the intersection is according to the domination tree order, or the domination order basically. So we are going to recursively construct this IDOM relation or domination tree using this equation. So we are going to use a naive algorithm, which is repeatedly refining this immediate dominators. But there is a much more sophisticated algorithm which is beyond the scope of this course. And we discussed that we are going to construct this domination relation using what is called reverse post order, which has a very good property that if B is, if A dominates B, then we know that A should be ordered before B according to this reverse post order. We already discussed how to deconstruct it, and we're going to see actual code that constructs this RPO. Now, using the notion of a domination relation, we are going to define on what is called a dominance frontier. So its meaning is that y is at dominance frontier of x if and only if y is at the frontier of the domination of x. So y itself is not dominated by x, but it is just becoming undominated by x. So that's the meaning of this dominance frontier. So more precisely, y is in the dominance frontier of x if it is not itself dominated by x. As a result, x is not the dominator of y. And at the same time, there is a node block z, which is actually a predecessor of y, that is itself x, or it is dominated by x. So think of it. Z is either X or it is dominated by X, as described here. And Z is also a predecessor of Y. So it is dominated, but Y is not dominated. So between this edge from this Z to Y, Z is dominated and Y just becomes undominated. And that's the notion we want to capture. If that is the case, we are going to say Y is at the dominance frontier of X. So it is used in the compiler optimization and control graphs in this way. So the validity of a register, say %x, ends at its definition's dominance frontier. So if you want to prolong its lifetime, you have to insert a phi node at the dominance frontier. So it happens for the register promotion. So suppose that a store instruction is happening at some point of the program, but its validity should end the store instructions dominance frontier. So if we want to maintain the invariant of the stored value, we need to insert a phi node. So that constitutes the mem2res algorithm. So we are going to calculate the potential positions for which we have to insert the phi nodes, and this is basically the dominance frontier of the stores, basically. So this is the more precise definition of the algorithm. Let's say X is the set of stores to a promoted location L in register promotion optimization, and we may need to insert phi nodes at a dominance frontier of X, and these are inserted with phi nodes, and they in turn may require additional phi nodes, which is located here, the dominance frontier of X. Maybe we have to insert phi nodes there too, and so on and so on and so on. So these are the potential positions for which we have to insert phi nodes, but all the other blocks are not necessary to insert phi nodes, on the contrary to those in the dominance frontiers. So basically, that is the high-level algorithm for mem2res optimization. And here's an example. Let's say A is the initial block, and here we are going to load from P. Let's say P is a location, and here we are going to store for it to P. And we are going to jump to another block P. And depending on some value, we are either going to C or going to D. And in C, we are going to store 37 to P, and it is immediately jumping to D. And D, we're going to load from P and jump to E, and E is also reading from P, and it goes back to B. So then let's say that let's assume that these P are only used as read-write pointers, and it is programmable. And we want to replace the load instructions with the value, basically a register value. So the algorithm proceeds like this. So we are collecting the set of stores for the location P. It is A and C. So there are store instructions in the blocks A and C. Now we are going to calculate those blocks for which we may potentially insert phi nodes, which is the dominance frontier of this, and dominance frontier of this, and blah blah blah. Actually, when we calculate this, it is the set of D and B basically, because A's dominance frontier is empty. A's dominance frontier is empty set because everything is dominated, and there is no such frontier of domination. Nothing is not dominated by A, so each domination has no frontier, basically. On the other hand, this dominance frontier is B because D dominates E and E has edge to B, but B is not dominated by D. So yeah, that is basically the yeah. Oh, I was confused. So we have a store as C, and C's dominance frontier is D because C has an edge to D, and D is not dominated by C. So C is itself, and D is not dominated by C because it is dominated by B, and there is an edge from C to D. And as a result, D is the dominance frontier of C. Furthermore, B is the dominance frontier of D because um, because D dominates E and E has an edge to B, and B is not dominated by D. So the meaning is that this domination ends at this edge. D dominates E, but not B. And as a result, B is at the dominance frontier of D. So when we calculate the the potential positions for finals, we can get the set of D and B here, and we marked it with the blue ribbon basically. And we are going to traverse all the blocks in the reverse post order. And in this example, we are going to say the reverse post order is A, B, C, D, E. This is basically the natural order from the graph here, A, B, C, D, E. And we are going to traverse all the blocks like this. So at the beginning of this block A, we know that the initial value of stored in the P should be undef value because nothing is stored so far. So the value should be undef. And phi node is not inserted at A because the potential position for phi nodes are D and B, and as a result, in A, the initial value should not be the phi nodes of A. And no value has been stored so far, and as a result, initial value for A should be undef. And we scan this block, and we can see that A should be undef because it is the initial value is undef. And later, we are going to store 482 to P, and as a result, the final value stored at P at the block A should be 482. So we can deduce this by scanning this block. So in the meantime, we deduce that %A should be undef. Okay, so far so good. And let's move on to the block B. And initial value of block B should be the phi node of B because a phi node should be inserted here, and it is the first value that is meant to be the stored value of the stored value at P, and as a result, we are going to say that the initial value at the block B should be the phi node value that should be inserted at B for the location P. And we scan the block, but there is no loader stores, so we just conclude that the final value of B should be the phi node of B. And let's move on to the block C, where the initial value of C should be the final value of B, because B is the immediate dominator of C. So there is no block in between B and C, and B. So we can immediately deduce that C's initial value should be B's final value, because we have to jump from B to C basically. And we scan the block, and we can see that the final value of C should be 37 because we met a store instruction here. And let's move on to block D, where the final should be inserted. At this point of time, we can see that the initial value of D should be phi node of D. Phi node for the location P that should be inserted at the beginning of block D. So we are going to say initial value of D should be the phi node of D here. And we scan the block and we deduce that %D should be the phi node of D. So here the phi node should be inserted and its value is the same with the %D register here. And finally, the final value of stored at P from the block D should be the phi node of D because nothing has been stored in this block. And similarly, for block E, the initial value for block E should be the final value of block D because D is the immediate dominator of E. And here, in order to reach E, you have to go to D first, and as a result, the initial value of E should be the final value of D here. In more general, if no finals should be inserted at here, then the initial value of this E should be the final value of the immediate dominator, which is D in this case. We again scan the block and deduce that %E should be the final of D, and the final value at E should be the final of D. So far so good. We scan all the blocks and deduce the initial and final values at each block. When we also deduced which value, I mean, what should be the loaded value for each load instruction. %A should be undef, and %D should be the final inserted at D, and %E should be the final inserted at D. And using this information, we actually insert the finals. So here, we need to insert the finals here, finals at D, because it is actually used in the loaded instruction. So we are going to insert the phi node at the block D. And here we are going to introduce a new register. Let's say it is ampersand phi D, and its value should be given by the phi node instruction here. So it is the final value of B if it jumps from B, or it should be the final value of C if it jumps from C. So it is just the formula here. It should be instantiated with the final values from the predecessors B or C. And let's look at what are the final values at the block B and C. So final B is phi node B, so it should be a phi node B here. And final C is 37, so we are going to insert a 37 here. So all in all, the ampersand phi node D should be either phi node value of B if the control flows from B to D, or it is 37 if the control flows from C to D. Now, in turn, we are observing that phi node value inserted at B is used in this instruction. This phi node instruction will be inserted, and it requires the phi node value of B. And as a result, we are going to insert a phi node to block B as well. And similarly, it's defined like this. It is a phi node of the final values of the predecessors, which are either 42 if the control flows from A, or the phi node of D, when the control flows from E. But phi node D is already inserted, so we no longer need to insert more phi nodes. So it is the five node formula we need to insert at D and B. Now, after deducing all the equations, we are actually replacing the load and store instructions basically. So first thing to do is that because thanks to the fact that we deduced the equations for all the load results, we are going to replace them. Oh, ampersand A should be undef. So we are going to replace all the occurrences or all the uses of ampersand A with undef, and we are going to remove this load instruction. Furthermore, we know that this ampersand D should be the phi node of D. And as a result, we can safely replace all the uses of this ampersand D with ampersand phi node D, which is not yet inserted so far, but which will be later inserted, just in a minute. Similarly, ampersand A should be replaced with ampersand phi node D, and these instructions can be removed. And after that, we are going to insert a phi nodes like this. So these two instructions are the direct translation of this equation here. Ampersand phi node D should be a phi node of either ampersand phi node B or oh, this is a typo. It is 37. And ampersand phi node B should be the phi node of either 42 or ampersand percent 2, ampersand phi D basically. So after inserting these two instructions, everything is well and the optimization is done. So after that, we are going to remove all the store instructions to the promoted location P because they are no longer used. And in our implementation, we just replace them with a nope, which does nothing. And furthermore, as we discussed just before, all the load results will be replaced with the equations, the variables here, and all the load instructions from the promoted locations are replaced with nope because load does nothing. Load means nothing in the optimized program. So this is basically on what's going on in the register promotion optimization for a simple example here. So this algorithm can be used to more complex counterflows as well.